Take a look at this model right here. You'll notice this is the model of a video I shot earlier about achieving locations of ledgers when you have two different pitches and you don't know where it's going to end up. So you'll see this is a 12-12 pitch on this side here, and it's been shifted over, so the center line of this 5 foot by 5 foot model has been shifted over 18 inches. So here's the center line here, and that left from the center line of this hip, where it would normally be on the corner here, 18 inches from the corner. So we lost 18 out there and we gained it out here. This is a 6-12 pitch roof here on the front of it. This is a 12-12 here on the two sides in the front and the back here, and it planes across here. You see this right here? So if this side was sheeted, there would be no bumps at all because this planes in. In order to achieve that, this bastard hip has to match the heel stand on this left side as of these common rafters here and of this left side heel stand on the standard hip that runs down here. This heel stand on this side would be on the same as this one if there was a wall running across. In other words, if this was shifted out here and it turned the corner, the heel stand on either side would be the same. But since it's slid over and you have an interesting cut underneath this, a side cut underneath this rafter here, heel cut, we're only using the heel stand on this side in order to blend in with this one. That means that this thing has to, where the side of the rafter runs through the plate line, match that of the standard hip. Enough said. Now, the heel stand on this bastard hip is different on the right-hand side than the left-hand side because it doesn't bisect the corner like a standard hip does. That means that pitches on either side are different. That is to say, in plan view, the angle on either side would be the same if it bisected. This one, since it's a 6-12 on the front and a 12-12 on the side, swings over, and that would change the side cuts when it ran through the plate and change the heel stand. So all these 6-12 common rafter heel stands have to match the side, the right-hand side, and all these 12-12 heel stands match the left-hand side, or vice versa. They match the common rafters there. What happens here with this plate height difference is that if this common rafter run were to swing on out like this, the hip would come down and meet it on an imaginary corner 18 inches out there, right? Same amount as over here because we slid it over. We lost that 18 inches. So that means this plate length is 18 inches, right? Because it would swing out 18 inches, right? Well, if this is 18 inches and it's a 12-12, it means the rise is 18 inches, right? And but all we would need is this run in order to find this rafter length, because we'd multiply it by the common rafter secant, or line length ratio, which for a 12-12 pitch is 1.414. Now, knowing that this is 18 inches long, that plus this plate length will give you the run of this one here. And how do we know that? Well, we know it because if we swung it out 18 inches, then it would be the same amount as it is from the center line of this one to the center line of this standard hip, where it was going to change direction here because the whole thing slid, right? So this plate length plus this plate length would be the run of this common rafter, but not to mention it would give us the location of the center line here. And then we know the span, subtract the 45 thickness of a common rafter, which is 2 1/8, probably with build up 2 1/4, divide it in half, that'll give us the run for this, which we already know what it is, and multiply it by the 12-12 pitch secant, or line length ratio, which is 1.414. That'll give us this length here. And then where the side of this common runs into the side of the hip there, this side here, which is common in roof framing. We want to deal with the sides of the rafters. When it's drawn out, it's just a skinny line with no thickness at all, but once you get some thickness involved, we want to start operating on the same side, right? On the West Coast, we use a skill saw. We are always to the short point, so we want the short point side, this side here, to figure out the common difference of these jacks here. So, turns out here I have this stacked at 12 inches on center, so there'd be more rafters in a smaller model, right? Well, that would be 12 times the line length ratio or secant of the 12-12 pitch, which is 1.414. That would give us 16.97 or 17 inches from the short point of the double cheek cut on this side. If we measure down and then measured from the bottom up, that would give us the length of this one here. If we did it again, 16.97 or 34 inches shy, measured that would give us the short point of this one here. So we would have all of these, right? All these rafters. And that side there is the same, so we don't have to worry about that. Now I'm not going to talk about the hip lengths right now. Talk about this finding the run, like a video I shot earlier, of these lower pitch rafters, which are 6/12 pitch rafters. How do we find the run? Now, remember I slid this thing over 18 inches, so we know that from the outside to the center line is 18 inches, but we want to go to the side of the rafter, right? So we subtract the 1 inch, it's inch and a 16th, we call it 1 inch, and that'll give us 17 inches from this space to its outside corner there, 17 inches. Now, there's a ratio between these two pitches. This is a 6/12, and this is a 12/12, and 6 is twice that of 12, so the ratio is 0.5 and 2. How come? Because if I drew a rectangle that was 6 by 12, one side would be twice, the 12 side would be twice the 6 side, and the 6 side would be 0.5 of the 12 side. So the ratio is 0.5 and 2. This is really important. Use that over and over for these split pitches here, right? Why do I want to know that? Well, it's because it takes a 6/12 rafter twice the run to achieve the same height as a 12/12 rafter, right? Twice the run, right? So that means that if I want to achieve, if I started here, it would take me what? Whatever it took to get up to this point, from here to this point, it would take twice that to get the run of a 6/12 pitch. What do I mean by that? What do I do about that? Well, I measure this right here from the outside to the side is 17 inches. Double it, 34 inches. That will give us consistent height here. And that'd be the location of this ledger. And that'd be the run of these common rafters. Multiply the common rafter line length by 34 inches, and that'll give you, which is 1.118, 6/12 common rafter, that'll give you the length of these commons here. Now, where does that ratio come into play again with common rafters? And I'll tell you, if you look straight down on it, you'll notice the layout of these jacks on this side of the hip is different than this one. That is to say, they don't line up, right? The space from the short point to where they meet may be the same, but one rafter is a lot longer than the other. Well, the answer is the run of the low pitch is twice that of the high pitch, which is 0.5, right? So there's the ratio again. So I would measure from where the side of the rafter ran through the plate to the short point, always to the short point with the skill saw on the West Coast, right? Or, worm drive on the West Coast. Half of that would give us the run of this common rafter, 12/12 multiplied by the secant, or line length, which is 1.414, gives you the length of this jack rafter here to the short point. And then same with this one, where the side of this one, this side of the bastard hip runs through the plate here, right, to the short point. In this case, it's cut square here. I'll talk about that in a minute. So whatever you prefer, the short point or the long point, that is to say, it's not going to be a short or long because it's cut square, but the far side or the close side, always go to the close side. Twice the on-center spacing here will give you the run of the low pitch side. So if this is 12 inches, the run will be 24 inches, and then multiply it by the secant for a 6/12 pitch roof. Line length ratio, which is 1.118, will give you these two jack lengths here. Now, when you look down on it, so let's talk about that box. It's 6 inches by 12 inches, and you draw a diagonal line and you measure the angles. You're going to come up with a 26.5 degree angle, and I think 90 minus 26.5, I think is 63.5 or whatever. It's a long, skinny angle here. Now I have a swing table over there will achieve it, but this is a lot quicker. If you go from the same side to the same side, and with a block, and you cut the shallow pitch on it of the two, which is 26.5 degree angles, which is the same as the high pitch jack rafter side cut, and you butt it up to the hip. That'll give you exactly where this one stacks, but also this one you don't have to cut an angle on it. Just cut it square plumb cut, and you get these two will stack without some fancy saw, right? There you have it there. Now, this one here, if this one ran all the way out to here, that would be 17 inches less than this length here, right? So measure down 17 inches from the long point. Now, that is to say, measure up 17 inches. Whatever's left over, minus this ledger thickness, would give you this one here, because this is dying on that side of the ledger, and these all common rafters are stacking on this side of the ledger, remember? This is 34, that would be 17, remember we doubled it? This would be 17 to plate, if this was to turn the corner. This can seem more complicated than it is. You need words to convey these ideas, which are complicated in their own right. And when you come here and you turn the corner here, remember we said whatever that was, we were twice that to the ledger, right? So that'd be 17 inches, and then this, and then the difference would be the length of this, but then on the level you'd have to subtract 1.5 inches for this ledger. And you wouldn't measure 1.5 inches along the top of the rafter. It has two plumb cuts have to be drawn 1.5 inches away from each other, and you cut the upper one. That'll be the length of this one. So we have the lengths of all these, this one, all of these, you even know these block lengths. How do you get the ledger length? Remember that 17 inches? This ledger, if this ledger was the same length as this whole model, it would be 60 inches, right? Remember we go 17 from the outside of the building, 17 inches to get to the face of ledger. This face of ledger, remember? Well, anything that happens in one direction on a 45 degree angle happens in the other, right? Like your speed square, you look at it, both sides are the same of it, as it, right? So whatever happens here, so that means you subtract 17 inches this way, you subtract 17 inches that way, so on either side. So you take 60 minus 34, that gives you what, 26, from long point to long point on the outside. That's how it's long point to long point. You use one of these common rafters to stack this ledger, which you'll find it stacks really high, but most importantly, it planes in, because common rafter can cinch up and down with the low pitch. You wouldn't even know, 1/4 inch. You got to stack your ledger this way first, bring it up to where it goes on either side, tack it, and then put your common rafters in, and if there's any error, it'll be down here, you know. There won't be any error, but if I put it up there tight down below and tight up here, and I just went like this, boom, I could go down 1/4 inch, you know. So you put it where it goes and fire it off, right? It's not going to be a gap. But I can have even less of a gap by going whack, you got it. So yeah, this planes in. So remember I said about the, we achieve this length here. This side cut and this side cut are the same. So the side cuts of a jack on a bastard hip or valley is the same as the side cuts of the bastard hip or valley itself, 26.5 degree angle. Why is that? Because the way you achieve the hypotenuse of a 6/12 is by drawing a box. It's 6 inches by 12 inches, and then drawing a line diagonal line and measuring what that is. Right. In this case, it's like 13.4 or 13.6, the diagonal. And then a rise of 6 inches in the hypotenuse. If you divide it by 12, that would get you y divided by 12. Rise of 6 inches, right? Because that's all on, that's the plan view. 6, 12, diagonal, that's in plan view. But then you got to get some rise, right? 6 inches of rise. The hypotenuse is the rafter length for every 12 inches the common rafter runs. Divided by 12 to put it in inches. So that if we have a span that's 173 inches, we just multiply that number by it and it'll give us in inches. Because I operate in inches, not feet and inches. Too complicated. You start operating in feet sometimes, in inches and other times. 60 inches could be 6 feet. 5 feet, which is 60 inches, could be 50 inches. Too complicated. Stick with inches, I think. In my opinion, we always have. That's how I came up. So yeah, stack this ledger. But anyway, once you achieve this length, right, by doing the miter rule, which there's earlier on in these videos, talk about the miter ruler. I need to talk about it some more. Once you achieve this, you'll find one side's 26.5, the other is a 63.5 degree angle, I believe it is. Side cut. You can get it with a swing table, or you can run your saw along the face at 90 and cut it like that. It's not that accurate. All I know is that the side cuts, if you land on the corner, that is to say the heel stand, if you land on the corner, are going to be different. This one's going to be higher than this one. Lower, I mean. So these heel stands are all going to be lower than this one. They're just going to stack where they stack. One side of this is going to be lower than the other side because it's at an angle. It has a side cut on it. What else is there? There's this. I'm beating this up. Martinez square, aircraft aluminum, super hard aluminum. These slide up and down. Using it slide up and down, it's a pretty good tool.